Hello, everybody. This is Square Pegs and Possibility. We are here going to go over a course, the first lesson of a course, Closed Conduit Pressure Flow. That's the course. The lesson is continuity. This will act as a basis for some of the more complicated calculations as we continue. So, if you know anything about how we prefer to go through the lessons, we like to jump right in. So I'm using a stylus and a screen, so bear with me. I'm going to do my best. I think it's going to keep up and do well, but we hope to get the point across and go through some fun examples. Okay. That being said, the basis of continuity is right here in this illustration. Okay. Really what we're talking about is the flow in, or the Q in, is going to be equal to the Q out. So in this particular case, we're looking at a pipe of some diameter, which is smaller than the second diameter, and we have a sudden expansion in diameter. But all the while, the flow in is going to be equal to the flow out. That's the basis of continuity. Sometimes we look at that across a length of pipe. Sometimes we look at that in a controlled volume, like a reservoir or a pool or a reactor. Sometimes we look at that, we draw the box, if you will, around a node where the sum of the flows in is the sum of the flows out. That's continuity. If we look at that a bit closer, the equation of continuity can be expressed as a mass flow rate. This is important. It shows up on the exam. That's why it's here. I try to weave theory in when appropriate, but really this is about the PE exam and passing it, particularly the civil, and more specifically the water resources environmental PM session. So if we assume that the mass in equals the mass out, and mass is the density of a fluid times the cross-sectional area of the pipe's flow and its velocity, then density area velocity is going to equal density area velocity. However, if the fluid density does not change, or if it is a incompressible fluid, the equation could be modified to a volumetric flow rate, Q in, Q out, or V, the velocity times the cross-sectional area, in equals that of out. You could see the units. Units do change, but these are common units that you'll see in the exam. The standard, as opposed to the metric, is where you can bet for exam purposes. However, keep your unit conversion tables handy. That's my suggestion. I'll typically solve and then convert at the end. Nonetheless, exam hit here. If the diameter remains constant, so does the velocity. Think about that. If the diameter doesn't change, therefore the area doesn't change. If that doesn't change and the flow stays the same, then the velocity must also stay the same, correct? Just worth noting. Okay, so taking this concept over to the next level, flow can also branch, and in this case down here you'll see something along the lines as a flow coming in, and you have 1 and 2 and 3 different flows coming out. This is Q1, Q2, Q1, Q2, Q3, and Q4. So in this particular case, the flow in has to equal the flow out of the entire system. So Q1 is equal to Q2, Q2, Q3, Q4, as shown in the equation here. Pretty simple stuff. It's your basic mass balance. I'm assuming that this is intuitive to your work and your educational background. However, this stuff shows up on the exam. Sometimes it's simple, sometimes it's tricky. That being said, we are going to take a look at an example problem at this moment and put some of the notes to work. So example 1, 10 cubic feet per second of flow right here is making its way through the pipe. We can see that the pipe diameter is changing. We got a 24-inch diameter in section number 1. We have an unknown diameter in section number 2. We have an 18-inch diameter in section number 3. All the while, Q remains the same. So that's the information provided. What is the velocity in the first section of the pipe? Very simple. We know that Q equals VA. Therefore, we know that V equals Q over A. In this case, we have 10 cubic foot per second. That is divided by the cross-sectional area at 24 inches. And if you use the table that we provided for you to download, you know that that is 3.14 feet squared. So then the answer is 3.18 feet per second. And we put a little box around that, and that's the answer. Simple. Expecting it to be simple. Probably won't see something that simple on the exam, but there is a follow-up question, and this is the type of thing that you can see on the exam. From the previous image, what does the diameter of the second section need to be to triple the velocity of the first section? Okay, so we know that Q1 equals Q2. That's given. We also know that the velocity of number 2 is going to be equal to 3 times the velocity of number 1. There's your trick right there. That being said, we have Q1 equal to V2 A2, which is essentially also equal to 3 V1 A2, Q1 that being. So we have 10 cubic foot equals 3 times V1, which is 3.18 feet per second, times A2. Well, actually, we can scratch that. If we take it to one step farther at this moment, we can call that A2 pi d2 squared over 4. And we can solve directly for diameter. In this case, d2 is going to be equal to 1.16 feet. And we'll put a box around that. So these questions are rather simple. I mean, the math is simple, but for an AM question, we can definitely see something with that's simple with an element of a trick added to it. In this case, we saw that the question asked what it would take to triple the velocity of the first section, and in that case, we knew that was a 3 times V1. Okay, and that moves us on to the final example for this session. A 20-inch pipe carrying a mass flow rate of 1,000 pounds per second splits in a Y with an 18-inch leg and a 12-inch leg. The velocity in a 12-inch leg is 12 feet per second. Assume the density of the fluid is 62.4 pounds per cubic foot. What is the velocity in the 18-inch leg? So what we do here is we draw the picture. We know it splits into a Y. Well, you know what we can do? We can make that a little bit straighter. Okay, splits into a Y. So we know that we have a mass flow rate of 1,000 pound mass per second with a diameter of 20 inches. We go into a diameter of 18 inches with an unknown velocity. And we go into a diameter of 12 inches with a known velocity. Well, we can go back to the continuity. Mass flow rate in equals the mass flow rate out. That in is now equal to the mass in flow rate in the 18-inch plus the mass flow rate in the 12-inch. That means that it is also equal to the density of the V 18-inch A 18-inch plus density V 12-inch A 12-inch. So essentially, that means we have 1,000-pound mass per second times the density of water times V18, which we're solving for. The cross-sectional area of an 18-inch pipe is 1.77 feet squared. Take a look at your tables. 62.4, 12 feet per second velocity, and a 0.786 square foot cross-sectional area. Solving for the velocity in 18-inch leg yields us 3.78 feet per second. Definitely can see this type of a problem on the exam. I think what they expect the test taker to be proficient in is the volumetric flow rate and sorts of tricks as shown in example 2. What they don't expect the test taker to be ready for without thumbing through some of the books or materials that they brought and trying to get their hands on a way to approach is the mass flow rate. The mass flow rate can show up in different ways throughout the exam, but I've seen it show up in the, I've seen and heard that it shows up in the AM portion of the exam. So it's worth understanding how it works, how to identify a problem, where you need that equation to solve for it, and how to pick up any tricks along the way. So that is the first session. This is our first video. I hope you like it. If you do, please tell all of your friends and colleagues about our test preparation lessons, but please don't share or distribute the actual lessons. We are trying to create something here that will benefit our family in the long run while offering very inexpensive and very accessible test preparation materials. So we appreciate your time. Please send us feedback, and best of luck on the exam. We'll see you soon.